everyone, and thank you very much for the introduction. So tonight I would like to discuss about Mercury and the Martian system and two really ongoing and next missions from JAXA, the Baby Colombo mission and the MMX missions. So the idea is to...
Point here.
Okay. So the idea is to discuss why do we study planetary surfaces and why it's important to learn about every detail as we can about the surfaces. So first, I would like to put us back in the universe. So this is one of the deepest images of the universe that we have. It's around 10,000 galaxies that you can see here. Each dot, basically, that you can see is a galaxy. And so the universe contains about hundreds of billions of galaxies. Of course, we don't know the exact number, but it's just to give you an idea about how many galaxies exist. But then on each of the galaxies, so here is an example of spiral galaxies. So it's about what our galaxy, the Milky Way, would look like if we could go out and take a picture. And so every dot that you can see here is a star. And we can imagine that around each star that you have here orbits several planets. So it's just to give you an idea of how many planets and how many surfaces, and so how the possibility to find life we have in our universe. So we will not go into that much detail about life and origin of life, but it's just to tell you that when we study planetary surfaces, we learn more about the formation of our solar system and the formation of other solar systems, and that it gives us possibilities to understand and find the origin of life. So about solar systems and planetary system in general, just a quick recaps about the formation. So in space, it can happen that there is a perturbation, like an explosion, a supernova, and this can disturb the matters around, so gas, mostly gas and dust. And when they are disturbed, they can collapse under gravity, and then the material will start rotating and flattening, giving this kind of disk you can see in the second steps. Then, so at the center, the temperature increases, and then a protostar can be created. And then, when we start nuclear fusion within this star, we call it officially star. And then the leftovers, so the material spinning around this star, we start to agglutinate and to stick together to form what we call planetesimal. So you can have examples here. And then with increasing heat and material, this planetesimal will go to protoplanets around here. And then some events of differentiation will move the elements within these protoplanets. So the heavy elements, like iron, for example, will go to the center, creating the core. And then lighter elements, like silicates, for example, will move and float toward the surface, creating the crust that we have here. So this is basically what we know for now about the formation of solar system in our universe. There is also something that we suspect is the repartition of elements in the solar system. For example, we suspect that heavy material and elements will condensate really close to the star, while volatile elements, which are lighter, will be pushed and will condensate at a colder temperature, so close to the end of the solar system. And this would be why we have terrestrial planets close to the sun, and then giants made of gas more far from the stars. But we'll see in a couple of slides that maybe this idea that we have about formation is not completely correct. Okay, so here we are on Earth in our solar system. And so today I would like to talk about how have the planets evolved since their formation with two different cases. And let's start with Mercury. So Mercury is the smallest and closest planet to the Sun. The planet was visited by two different NASA missions. So the first one was the Mariner 10 mission, which visited Venus and Mercury. The mission performed only flybys of the planets, like 3 different flybys, and we obtained images of the surface, only about half of the surface, so 45% exactly. Okay. And so after this mission, NASA sent another mission, the Messenger mission, which totally revolutionized our understanding of Mercury. So this mission was the first to orbit the planet, and it was extended twice until 2015. With this Messenger mission, we obtained images of 100% of the planet already during the first flyby of the mission. And then we obtained the color images of Mercury, which is what you can see here. So of course, this is not what Mercury looks like, just to be clear. Mercury is not purple and orange. This is just false color that highlights the surface differences. So let's zoom a bit. So this is a messenger morphology called image of the surface of Mercury. And you can see that the morphology is very diverse on the planets. So we can see on your right that we have very heavily cratered area compared to the left, for example. We can also see that if we zoom, we have different craters. We have craters which are very circular, that you can see here, and you have you have crater with no real shape and which are more or less deep, and nothing seems to be really organized. And those two different morphology will give us information about the evolution of the surface, because one will be more associated to potential volcanic events, while the other one is associated to impact craters. Moreover, we have some area, like you can see here, which are very smooth in comparison to other terrain here. And this is also important because we have to understand why those terrains are very smooth, why those terrains are really cratered, and so on. And this is when we start using physics and messenger data. So I mostly work with spectroscopy, and so I study the reflectance, which is the ratio between the reflected light and the incident light. So in the solar system, the natural light source is the sun, and then the sun will, the light will be reflected by the surface of Mercury, and this reflected light will give us information about the soil, about several properties like the grain size, and most importantly, the composition of the surface. And here is the enhanced color map obtained from Messenger. So it's exactly the same map as before, but you can see different colors. And here the colors, they highlight different composition, different ages, different grain size of the surface. And then we can try to better understand. So you can see, okay. So here you can see the two craters that we discussed before. And thanks to the spectral property, we know that they belong to two different events. And we can do comparison with what we know on Earth. Here you have two images of Earth, explosive volcanism on Earth and effusive volcanism on Earth. And then by doing some comparison, we can see that the crater that you saw just before with non-circular shape is associated to explosive volcanism. So such events could have happened on Mercury. And then within the crater, if you remember, the plane was really smooth with really low crater amount. And this could be associated to volcanic flows and lava, which just solidified after flowing, which is similar to what you can see here in Hawaii, for example. And then you can see that we have different color inside the crater and around the crater. And this was very hard to distinguish in the previous image. But here you clearly see that they are totally different, and this gives us information about what's below the surface. Because when a crater happens on the surface, it digs into the surface and then excavates some material from below. So this is very important because we can reconstruct all the stratigraphy of the planet. And this is thanks to all of this that this is the most accurate idea about what Mercury looks like in the inside. So basically, a really, really big core. So the core on Mercury is about half of the planet, which is very unusual. And then we could reconstruct several layers within the planet. So this graphite flotation crust corresponds to the very dark blue unit that you could see excavated by the crater. So it's this excavation that that led us to think about this layer that exists within the planet. And then with all the volcanism events that we found on the surface, it helped us to understand that Mercury, after the first crust, was modified with a secondary crust mostly made of lava. Okay. So now that we mentioned volcanism, we mentioned craters, so those are phenomena that we can find on other planets, like the Moon is also heavily cratered, and volcanism also happens on Mars, for example, or Venus. But there is something very specific to Mercury, which is the hollows. So you can see the very, very small hollows here, and here a zoom of these features. So these features is like, it's a flat floor depression, irregular, that is very unique to Mercury. So we were very surprised, and this also stimulated a lot of the extension of the MESSENGER missions. So what we think for now about the formation of these very specific units is that it follows different stages. So the origin would be some volatile elements from the crust that, because of heat or solar wind, or we don't really know, modify the surface and so create these irregular holes that extend with the amount of volatile which degas from the soil. And then the spectral property also changed, so you can see that they are very, very bright here in this image, so this is how we basically detect the hollows. But we also find some similar features with very dark properties, and it helps us to understand how do they evolve. And this is very important because we think if there is something active on Mercury, this is the features that is very active. And if you remember, I mentioned earlier in the solar system formation that we think that close to the star, there is less volatile elements that at the end of the solar system. And this is a big problem because we see with explosive volcanism and hollows that Mercury is really not depleted in volatiles, and that the amount of volatile is similar to Mars. And we thought during several years that Mars was the most volatile-rich planet. So we already understand that our understanding of the formation of the solar system is not totally right, and that we need to learn more about surfaces to correct our theory. But studying planetary surfaces is more complicated than just taking information and picture directly from the surface, because the surface is submitted to its environment. And for Mercury, very close to the sun, we have a lot of solar wind coming to the planet. And even though Mercury has a very, very small exosphere and a magnetosphere, the surface is really bombarded by solar wind and micrometeorites. And this will change the property of the surface. And I will just show you how. Yeah. So we call this phenomena space weathering. So it's a process which alters the chemical, physical, mineralogical, and spectral property of the surface of airless bodies. So like anybody with no dense atmosphere, like Earth, for example. And this biased interpretation of our orbital data. So space weathering, yeah, as I mentioned, it's like micrometeorite bombardment, solar wind, yeah, cosmic and solar rays. And so here is a study that we did in the laboratory. We put some rocks analog to Mercury and we irradiated them with helium, so like kind of to simulate the solar wind bombardment. And what you see here in the y-axis is the reflectance at a certain wavelength. And we see that if you follow the curve, the reflectance will change according to the irradiation. So here is the irradiation which increase, and we can see that the reflectance decrease. And this is very important because the property of the surface of Mercury that we obtain with orbital data, they are not the real property of the surface, but they are the property of the surface submitted to ion irradiation by the solar wind, for example. So we have to be able to take this into account in our analysis to really understand what the surface is made of. Okay, and so both Mariner 10 and Messenger, they raised way more questions than they answer, obviously, and so we still wonder, so what's the composition of the surface? What are the history and mechanism of volcanism on Mercury? What interaction between the surface and the environment, and so what's the space weathering regime? And also, where and how did Mercury form? Because it doesn't fit in our theory until now. And this is what was at the origin of the ESA and JAXA Bepi-Colombo missions. So Bepi-Colombo is a joint mission between the European Space Agency and the Japanese agency. So the mission is built with two different spacecraft. MIO, which will study more the environment and the magnetosphere of Mercury, which is the Japanese part of the mission, and MPO, which will focus on the surface of Mercury, which is the European part. And I will just show you quickly. Okay. Yes. The launch of Bepi-Colombo. So Bepi-Colombo was launched in 2018 from the French Space Center, like in Kourou, in French Guyana.
5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage 2AP, décollage.
So since 2018, the spacecraft is flying to Mercury. The mission is taking a bit longer than what expected, but should arrive into orbit by the end of 2026. Okay, and we recently had something, so the mission performed several flybys of the surface of Mercury, 6 in total. And during the last flyby, they could measure the sound of Mercury. So what you will hear now is the real sound of space around Mercury. So some instruments on board Bepi-Colombo already operate during several flybys, so we already have some data. Especially we have a lot of data from the study of the environment of the planets, and we recently had the first surface data in the infrared. Okay. So this is all for Mercury for now, and now I would like to discuss another system, which is the Martian system, and you will see how we can find the same problematic elsewhere in the solar system. So the Martian system, so probably everyone knows about Mars, so it's the most studied planet since years. It's the only planet where we suspect until now like really trace of life, and that we have several rovers on the planet, and we are now collecting some sample for future comeback to Earth. And so around Mars are two moons, Deimos and Phobos. So Phobos is the closest to the planets. It orbits at, I think, 6,000 kilometers from Mars. And then Deimos, which is way smaller and more far from the planets. And those two bodies are also airless bodies, so same problematics that Mercury. when we look at this graph, we can say, okay, it's well explored, well known, way more than Mercury, but this is not the reality, because some of the mission didn't work at the end, and also those are missions exploring Mars. So most of the data we have about Phobos and Deimos come from mission with the, that operates with the objectives to study Mars. So the two main missions are Mars Express and Mars, so from ESA, and Mars Reconnaissance Orbiter from NASA. And this is the morphology of Phobos. So here is a map kind of similar to the one you saw before for Mercury, but for the moon Phobos. So first, you can see that the resolution is not very accurate everywhere. There are a lot of area, like what's happening here, we don't know. We don't see a lot of detail. We can distinguish some craters, so we know that the moon is also heavily cratered, but still we miss a lot of information to have such resolution that you saw earlier on Mercury, and that could help to understand what happened on the planet, on the moon in this case. About the spectral data, so same, it's very poorly understood until now. We have at least two units on Phobos, a red and a blue unit. The blue unit is the brightest at the surface of Phobos. But we now miss a lot of information about the detail, because you saw previously on Mercury how much detail we can have on the surface. And here, for now, we only knew like two units, red and blue units. But of course, we are all convinced that some subunits exist, and that we need this information to reconstruct the evolution of the surface of the moon, as we did for Mercury, for example. And so, as Mercury, with no magnetosphere and no atmosphere to protect them, the moons are submitted to space weathering. And for Phobos, it's a very, very specific case, because it's submitted to solar winds, okay, like as Mercury, as asteroids, but the very particularity of Phobos is that it's also submitted to bombardment from the atmosphere of Mars, because it's so close to Mars that charged particles coming from the atmosphere of Mars reach the moon, and so can bias the surface. So here you can see that the repartition of the solar wind and the ion coming from Mars are not the same, which complicates all the process to understand how those irradiation modify the properties of the surface of Phobos. And here it's an example of a simulant from Tokyo University. They created a powder which replicates the surface of Phobos. And this powder was irradiated in, let's say, in the condition of solar wind and in condition of the atmosphere of Mars. And we can say that the properties are totally different. So basically just keep in mind that different colors represent different irradiation, and we can see that they are both different, so the yellow and red are very different from the pristine one, which is the one not irradiated. So the data that we will obtain in the future from Phobos, we have to decouple them from the impact of the environment. Otherwise, everything is biased, and we will not measure the good properties. And so why do we really want to understand the surface of Phobos? Well, it's basically because for now we cannot explain the formation of the moons of Mars. So we cannot explain the formation of the Mars system in general. So there are two main hypotheses about the formation of the moons. The first one is the capture. So that would mean that the two moons would be asteroids or comets that came too close to the planet and so were captured by the planets. This is confirmed by the spectral property that we have for now, because they really look like asteroids. However, all the dynamic parameters that would explain the position of the moons points towards another theory, which could be a giant impact. So this is similar to the formation of the moon and Earth, like same hypothesis, like a giant impact, and then accretion of material around the moon. But this is very hard to explain because the property of the surface of Phobos and Deimos are really different from what we would expect if this scenario would happen. So there are pro and like there are different theories. There are good reasons for each theories, but the result is we don't know how those moons form. So we don't know how the Martian system formed. So how can we pretend that we know about the solar system if we don't even know like the closest planets that we have in the rocky planets around us? So yeah, so what's the origin of the Martian moons? What's the composition of the surface? Do Phobos and Deimos have a similar composition and origin? We don't even know this first step. And so how did Phobos and Deimos evolve? What is the degree of space weathering modifying the surface? And this is what motivated another mission, this time only from the Japanese Space Agency, which is the Martian Moon Exploration Mission. So it's a very, very exciting mission that will be launched very soon, so almost at the same time as the orbit of Bepi Colombo. So a really exciting time this couple of years. So the mission will be launched and then will orbit Mars and come very close to Phobos. There are different steps in this mission. So they will, we will have remote sensing data from very, very close. So very good quality data of Phobos. We will also have IDEFIX, which is a small rover that will land on Phobos and will just take information about the surface of Phobos and move and also select very interesting area for the spacecraft to come and do at least one, but maybe two touchdowns that will take some material and then send them back on Earth in Australia, probably in 2031. So this will revolutionize our understanding of the formation of the two moons, and so of the Martian system, and so of the solar system, and so of other solar system, and so probably about life in the universe and formation. So I want to show you this. Okay.
I can try to play from here.
Okay. Yeah, this is a very short video from JAXA to advertise the mission. So yeah, you have the different steps. So this is an MX. So when the spacecraft will land on Phobos, it will stay something like 2 hours or so to collect the sample and then go back to space. So in this mission, there are also some new technology, like the IDEFIX rover, that will ride the surface of Phobos. And they're very, very low gravity, so it's the first time, and we'll see how it works. Yeah, so this is the touchdown, and then some instrument and arms, exactly, will go out to collect some samples. And the area for the touchdown will be identified by IDEFIX, the small rover that will select the best area. And so then the sample will be back on Earth for us in the laboratory to study the properties of the rocks and finally have a better idea of the composition, the effect of space weathering, and so on. Yeah, and this will end in Australia. And yeah, so I'll finish here just for you to keep in mind that somebody in the solar system remain very poorly understood. So we usually think that we know very well Mars and like why do we want to go back to Mars again and again, but this is also partially why, because we still have a lot of unknown. So a better understanding of their surfaces and environment is essential to reconstruct their formation and evolution. This is also why we don't do only ground-based observation, but we need to go there and even to take some material. And so this is a crucial step toward a deeper understanding of the solar system's formation and extension of that to other planetary systems. And JAXA is leading several space missions to achieve this objective. And thank you very much, and I'll be happy to answer your question.
Right. Thank you, Emma, for a great talk. So we have some time for question and answer, so please raise your hand and I'll call on you. So first question back there.
So you played the sound which showed the sound of space around Mercury. I was wondering if you could tell us a bit more about what actually are those sounds that we're hearing?
So this is not, I don't think it's exactly the proper sound around Mercury. So it's instruments that collect like waves and data, and then they translate those data into a sound that we can properly hear with our ears. So it's not like, I don't think we will hear this if we were on Bepi Colombo, for example.
In this case, no one can hear you scream.
Yes.
Yeah.
Thank you.
Yeah. I wasn't clear about the construction of the surface. What materials are in are what the surface is made of.
Mm-hmm.
You said that they've made a simulation of the surface in order to irradiate it. But how did they make that material?
So, which one? Like there is this one?
I think it was both.
Okay.
Yeah.
So this one, so on Mercury we have an idea about what the surface is made of, which is basically lava. So for this study we took some lava from Earth that are the closest analog. They are not perfect analog at all, but they are the closest we can find on Earth. So we used those rocks, and we
How do you know that they're close?
So because
Is that also a spectrometry thing?
So several parameters. So the morphology. So with the morphology, we can have an idea that okay, probably the rocks on Mercury are lava. Then we have a couple of compositional information. We don't have the full planet, but we know that the rocks are very rich in magnesium, for example, and this is close to basalt that we have on Earth. Then the surface is very dark, which is also a clue towards maybe this is a basalt, and so this is how we reconstruct. But we know that the volcanic rocks used in this work, we know that, for example, the composition in iron is not good for Mercury, but we do with what we can, and then there are a lot of ongoing study that works to produce better analogs to try to have all the parameters that we know focused on one synthetic analog, because we cannot find it on Earth. And so they work to find like the best analog, and then we will use those analog to replicate the same experiment to go closer to the surface of Mercury.
So for Mercury's case, you're
Yeah.
using some kind of lava rock from Earth?
Yeah,
Okay. And then
in this case.
in Phobos' case, you're
So for
Maybe something
Phobos, it's
really complicated.
yes, it's complicated because we have no clue about the composition of the surface. It's
Right.
not like Mercury. We at least know that it's rich in magnesium. In Phobos, we just have no clue. So they work on spectral analogs. So they try to build a powder which will replicate the shape of the spectra of Phobos.
Okay.
So yeah, and then so this is for this example, which is a synthetic analog, but we also work with meteorites. For now, the best meteorite analog would be some carbonaceous meteorite. Probably if we consider the capture hypothesis for the formation.
I see.
So everything is a bit vague for now.
So yeah, and that's also compared to samples that we found on Mars
Yeah, for do you mean the
for the material composition.
yeah.
Okay.
Yeah. So yeah, once MMX will give us remote sensing data from the surface, we will have very easily more accurate analog that we will build and find in the laboratory.
Two questions. First, how do we know like the size of the core of Mercury? I mean, we haven't landed it yet, but like, how can we like, estimate how like large the core is? And secondly, like in our current understanding, is the core of Mercury like a molten one, or has it already like dried up?
So we think both. We think there is a solid part of the core and a melted part, similar to Earth, because this is the way that we think the magnetosphere is produced around Mercury. So it's probably due to convection or movement within the melted part of the core of Mercury. So we haven't been there, but we just suspect that this magnetic field is produced internally inside the planet due to this movement. And then about the size of the core, so I actually don't remember in detail, but first the density of the planets. So we cannot explain such a density for such a small body that if it's made of iron and EV elements. So this is, I think, the biggest reason for this theory.
I guess in the future maybe we have to like put like a lander to like measure like Mercury quakes or something.
Well, I wish I can see this in my life.
Question back there.
Hi. Can we not do visual spectrography instead to understand what are the elements inside the surface? Laser spectrography kind of thing?
From Earth, it's very complicated. So
Not from Earth, but let's say a spacecraft enters the atmosphere,
okay.
orbits the planet, and then we do the spectrography.
But spectrography, like, what do you mean?
I think it involves bouncing a laser and see what wavelengths comes
Yeah.
back.
So I don't know if it's possible also because of the exosphere, or we have to go very close
Okay.
to the surface. I actually don't know. Sorry.
Me, right?
Yeah.
Your comment earlier about the Bepi Colombo mission taking longer than expected to arrive was very intriguing. And then when I realized later that it takes only 10 months to get to Mars, but apparently like 8 years to get to Mercury, I realized I have no intuition for orbital dynamics. So I was hoping you could help me a little bit.
So I cannot help a lot. I can just say that so to go to Mercury, we have to use like Venus, for example. We did several flybys of Earth first, then of Venus to have more power to go towards Mercury. Like, I think it's mainly question of feasibility and cost that we use several trajectory to, so probably he knows better, to reach Mercury. So we cannot go, and also because we have to avoid falling into the sun. So we have to, yeah. To know better, but maybe they know better than me about dynamics because
So there were some maneuvers along the way to get to save the initial launch cost or something. But what about the part about the trip taking longer than expected?
So we had problems with the spacecraft. So we don't have. I think now like the power is a problem in this. So we always have margin when we create the mission. But we have to keep a certain margin for the orbit insertion, and like we had a problem with the power. I think to go. Maybe you know better, but we had a problem of power to reach the surface, so we have to slow down and change the orbits. So this new orbit was the only way to go safer towards the surface of Mercury, keeping like a decent margin of error and the needed power to then go into orbit at the end. So it was postponed a year ago for a year.
I see.
Yeah, and so I think the messenger mission took 2 less years to reach Mercury, probably 6 years or almost 7 years, but it was more direct trajectory.
So is that something to do with the propellant on board to do the orbital insertion, or the?
So I think so. Everything is very precisely calculated from the launch because like the weight of everything has to be very specific. And then I think one of the, like it doesn't properly work during a certain period on board the spacecraft, and so we lost, like the mission was a bit deviated from the trajectory. We had to go into the reserve to go back. So everything didn't work perfectly, and I think that's why we had this problem.
So if you miss the initial insertion window, you have to wait a while until you get another.
I think if we miss the
Optimal.
insertion, we fall into the sun.
Oh,
So I hope we don't. I hope we don't miss the
No
insertion.
I see.
Yeah. Sorry.
Yeah, that's fine.
Yeah, normally when we launch to Mars, there is a window when Earth and Mars will be closer.
Yeah.
I think it's 26 months, I'm not sure. Similarly, there must be a window or time frame where Earth and Mercury will be close.
Then Venus will be close, and then Venus will.
No, Venus is being used for gravity boost.
But it has to be the same.
Right. But there is also a possibility that Earth and Mercury will be close and you can launch in that window so that the time distance between the two are very less, right? So wouldn't that reduce the time for the voyage?
So I don't know about all the dynamic parts, but I guess the launch at the most appropriate moment. And so yeah, the mission was postponed for years and years before 2018. I think almost 10 years or delayed before the launch. So
Okay, no problem.
Do you know what's used for propellant and for electrical energy generation?
I don't know.
In your slide about the introduction to Mars, there was like a word, like I think it was like liquid Roche limit and like a rigid Roche limit. But if possible, like can you explain the difference of those two? Like I understand that the Roche limit is like the limit where like the things start to fall apart due to gravity, but what's the difference between the fluid and the rigid one? I was wondering what's the difference of those two?
I'm not sure. I'm not sure. Yeah, what I wanted to show here was the distance of the moons, but I'm not sure about the detail.
I mean, I think it has to do with how well things deform, depending on how rigid things are. So, fluid rush limit would be exactly like where things, as you say, start to fall apart for like completely fluid bodies. But if it's, for example, like if you assume a rigid body like with uniform density, that's the rigid rush limit is for those objects harder than fluid things that are more dense than a fluid and more together.
I got a question about the graph that you just showed on the next two slides. One more slide, I guess. The one with, yes, this one. So I just want to confirm that, so the difference of reflectance, in case it is bombarded by He2 plus, then it becomes brighter, or could you please let me know more about what kind of graphic is this? What are the effects of the bombardments?
Yeah, so exactly. So in blue would be, okay, so if the surface of Phobos is similar to this sample, this is the reflectance property of Phobos. But this is like only if Phobos is not irradiated, so this is not realistic. So if the surface is like the blue spectra, in reality, if we consider the solar wind irradiation and the Martian atmosphere irradiation, no, or in this case, it's one or the other. This is more what we should observe. So this is just for us to give information. For example, when we study a spectra, here you have an absorption band, for example, and those kind of features, we study at which wavelength it happens, what's the value of the reflectance, for example, what's the broadness of the band, and so on. And this can be changed according to the irradiation. So, for example, so here it's very like variation are not as big as on on minerals that we can see. But if we expect a reflectance at a certain level and we have another one, this graph helps us to understand that, okay, maybe it's good, it's just because there is the irradiation, but maybe the material is good, it's just that it's the real condition. So this is just to be more prepared on how we can interpret the data, what's the composition, because all the property of the graph, we relate it to the composition of the surface. So for example, if we have an absorption, and according to the shape of the absorption band, we also reconstruct the amount of minerals, for example. So we will overinterpret the spectra if we don't consider the modification by irradiation.
Maybe one more quick question. Anyone has a quick question? Yeah.
A quick one. So I was wondering, so this information that we gather about the surface of Phobos or maybe the surface of Mars, do people at JAXA use that information to inform maybe design of like landers or other kind of spacecraft in the future? So this information we're gathering, do we use that to inform future missions on that might land on Mars or land on any other moons in terms of how we design and would choose where to land?
So so usually there are several steps. First we observe from Earth, then we go, either we do some flyby or we orbit. And then when we know already a bit the surface, we go and land or we take some samples. So in this case of Phobos, for example, so we know that there is a really low gravity on Phobos due to previous study. We also know that the soil is probably made of regolith, so really, really thin particles on the surface. And this is how we constrain the IDEFIX rover that we go on Phobos. So for example, for a rover to work, we need to fix some specific property, like the weight, the speed of everything, how will it work on the surface, and all those information, they come from previous study of the surface from, in the case of Phobos, other mission or ground-based observation. And also we need to be sure that we will not crash when we arrive, so for this we need to know like how is the surface, is it solid, is it like impossible to ride on the surface, or is it very very hard? And with all those parameters we will adapt the parameters of the rover.
Thank you.
I think we really did end our time today, so you can ask her afterward. Yeah. Okay. So thank you, Emma.